Let me introduce the team now. I'm Yogendra, and I'm based in Melbourne, Australia. I'm head of Future Networks in EA Technology. And two of my colleagues are joining from UK. It is 10 p.m. night there. Dr. Kate Thompson and Lawrence Hunter. So welcome both the speakers. And this webinar, please do type your questions either in the chat box or Q&A box. And we will endeavor to answer all the questions. If some questions are remaining, we will answer them, when you receive the recording. Along with that email, we will answer all the questions. So please feel free to type your questions in the chat box or Q&A. As I said, this webinar is being recorded and you will receive the recording after that. Next one, please. All right, those who have joined, we just starting. This is the agenda for today. So what we are talking, and we are talking of the distribution level curtailment. So what is the curtailment? Why do networks curtail generation? What is the need for that? And then we will be discussing what are the networks interested in curtailment modeling, the forecasting, and how important it is. And then there are national grid perspective, that national grid and EA technology working together. And there will be results from stage 1 and what's happening in stage 2 and what is next, what the plans are, and then some summary or conclusions here. So we will be discussing these points. The next, please. So I will actually just give you the Australian context and then Kate and Lawrence, they will give you mostly the UK context there. So what is the curtailment? In terms of, I'm just quoting a project which has recently finished. It was a very big project funded by ARENA, the Project Edge. And Project Edge actually tried various roles and market configurations like hub and other things, and saying how this all information can, work together to avoid the curtailment. And their finding was that it can avoid like 15 terawatt hours of customer rooftop solar curtailment to 2030 and 90 terawatt hours across the 20 years time horizon using the AEMO's ISP, the step change scenario. The dynamic operating envelopes, which we use in Australia, they definitely release more hosting capacity, or like they allow the using the capacity to the last drop. But that will definitely require a sufficient proportion of DER to be connected under the flexible connection agreements or curtailable connection agreements. The next, please. Now, in Australia, in 2022, the Australian Energy Regulator came up with the DER integration expenditure guidance note. And so this is basically harmonizing that information that every DNOs or DNSPs is trying their own methodology to saying what is the value of DER, hosting capacity, improving the hosting capacity. So in those terms, it has proposed a DER, value of DER and how to calculate that, like increasing the hosting capacity and what is the BAU, and that include the investment cost, operating cost, and environmental outcomes also. So this is the methodology AER allows the DNSPs here in Australia to use to justify the expenditures. The next one, please. Part of this same value of DER strategy, there is a piece of work which is saying customer export curtailment value. So that is where there is a value. What is the value of customer export curtailment? And that in the dotted line, what we are showing here is actually includes the essential system services like FCAS services. We avoid that. and avoided marginal generation cost and avoided transmission distribution losses. So that the AER is trying to publish the CECV value every year. And that becomes the basis or justification of that. If you want to avoid the curtailment, there is a value for it. And next one, please. Now, this is just an example. Recently, I think this was CECV edition 22-23. And this is a kind of every state, there is a value for curtailment. You would see that this is like goes up to the 75 to $100 per megawatt hour. So this is actually the actual report gives every half an hour what is the CECV for that. So people can then decide that if we are curtailing something, what is the cost for that, or we are avoiding the curtailment, what is the value for that? So in their calculations. The next one, please. So, I mean, look, recently, AEMO has come out the requirement for sub 5 megawatt DR connections. And definitely, AS 4777 is required here because that will allow the essential curtailment if required for system security. And the curtailment is the distributed PV. Here we are talking DER means at the moment is distributed PV. And to maintain the power system security, if all the options are exhausted, then curtailment will be the last measure. So, we are discussing why it is required. And it is required sometimes to either to active network management, the power quality, or to support the bulk power system. When there is a requirement for bulk power system, the AMO will direct the DNSPs or DNOs to manage that thing for them. So it is happening through the DNSPs. The next one, please. This is in Victoria, the emergency backstop mechanism. So because the newer inverters are actually following that AS 4777.2 2020, and then that Australia is using IEEE 2030.5 CCIP profile. So there is a possibility that third party or DNSPs or DNOs can directly control the inverters if required, from the distribution PV, rooftop solar PV. So Victoria is introducing an emergency backstop mechanism to manage this risk of, minimum demand, if you like. So when there is a lot of minimum demand, they are, in case of emergency, this scheme is being or is already implemented up to a point. So it was in 2 stages. And the emergency backstop will manage the mandated capabilities to remote curtail new and replacement of solar system as a last resort to manage the minimum system load emergencies and protect Victoria's system security. So we are saying, yes, there will be times when there will be curtailment. But, how much will be the curtailment? First, to forecast that, what is the value or what is the cost for that? So we will discuss all these things. The next one, please. I'll hand over to Lawrence now to discuss more.
Thank you very much. That's a really interesting context to so basically what we've been looking at with within the Australian setting. If we could just move to the next slide, please. So my name is Lawrence Hunter. I'm an innovation and deployment engineer at National Grid Electricity Distribution. We have an extensive network in the UK as the UK's largest DNO. We have around 8 million domestic customers. The network is about 220,000 kilometers long, and we have around 200,000 substations. And these range from small transformers mounted on poles all the way up to large transmission interface sites, which we call grid supply points. In the UK, there's 6 other DNOs, and within NGED, I represent the Future Capability team. And we carry out network innovation and deployment projects aimed at decreasing the cost of getting to net zero, increasing the reliability of our network, and keeping energy prices as low as possible. Our regulator, Ofgem, allows us to do a fairly significant portfolio of projects through regulated innovation funding. And as well as trialing new technologies and techniques, we also carry out research projects such as this, which aims to understand what future capabilities distribution networks need to have, what might be required in the future to overcome the problems that we've not faced yet, but are likely to do so in the next 5 to 15 to 20 years, and begin identifying what the best methods to address them are. Next slide, please. So one of the areas that we've been very interested in over recent years is the ability to increase the hosting capacity of generation across our network. And one of the methods in which we've made some very good progress within is the use of curtailable connections. So these accelerate the connection of renewables by allowing customers to connect ahead of traditional network reinforcement, with the acknowledgement that at times of system peak, they may be asked to reduce their export to keep the system within its limits. We first trialed active network management about 10 years ago within previous innovation projects, and it was quickly adopted as a technology used within the business as usual within NGED. And currently there are around 3 grid supply points that have A&M zones operational, and a further 15 are in development. In the future, looking ahead, we anticipate that around 18 gigawatts of connected generation will be managed through active network management across 650 generation sites. So just looking at today, the UK has around 30 gigawatts of distribution connected generation. But looking forwards to 2050, using NESO's, the National Energy System Operator, we see a growth of up to 120 gigawatts of generation connected at distribution networks. And without targeted increases in hosting capacity, the extent to which this low-cost, low-carbon generation can access the wider energy system is at risk, because we risk curtailing generation where it's needed most, and in the place of this low-cost generation, relying on transmission-connected gas peaker plants or interconnections to Europe. So the opening hypothesis of this work, shown on the right-hand side of the screen, is that if we can increase the share of renewable energy sources through increasing capacity across our network, we may displace this higher cost, higher carbon alternative through a shift in the merit order stack. On the next slide, you'll see that until recently, UK customers have spent around 30% of their energy bill on wholesale costs and around 10% on distribution network costs. Although recent increases in wholesale costs have increased this percentage split significantly. In 2021 and 2022, it was around 70%. But we see a much greater percentage of the UK energy bill going to wholesale costs than distribution network charges. So one of the things we're interested in looking at is understanding whether targeted increase is in hosting capacity, which would have to be paid for, may actually lead to a larger decrease in wholesale costs, which leads to an overall system benefit to consumers in the UK. Can I go to the next slide, please? So by the end of this project, we want to calculate and sort of develop a methodology that captures this whole system value of network headroom. And we're working with Baringa Partners and EA Technology to help us achieve this. This is above and beyond what distribution network operators are required to do in the price control sort of settlement of the regulated space. We haven't yet looked into the effect of our network on wider energy system prices before. And so it's a really interesting piece of work that's hoping to direct our future innovation activity to the areas that could have the largest benefit to the overall energy system. To help us manage risk across the project, we began this piece of work with a shorter sensitivity study, which aimed to capture the expected range of benefit across 2 scenarios. an upper and a lower bound. To start with, let's have a look at some of the results from this scene setting work before I'll hand over to Kate, who will provide an overview of our more recent investigations. So shown on screen now is the network forecasting methodology, which we used in our stage 1 work. So you'll see that we've got a few voltage levels across our network, ranging from the 400 volt LV network to the 11 kV network, which supplies our secondary substations, and the primary network, which is operating at 33 and 66 kV. We also have a 132 kV network, which operates across steel towers and underground cables. And obviously, we have an interface with the transmission system. Within stage 1, we employed EA Technologies' transform tool using 4 representative days to study the 400 volt to 66 kV network. And these 4 representative days included the winter peak demand, summer max generation, intermediate cool, and intermediate warm to establish an annual demand profile for generation and demand customers. Using the parametric model, we considered the entire GB distribution system in one study. This is not currently possible with current load flow methodologies available to us, as there isn't a model that could converge over such a significant network. And it was able to produce very scalable results. The results that we used through Transform, as I say, cover the 400 volt to 66 kV network. And we used this simple curtailment tool, which is an in-house forecasting tool that National Grid has developed to consider the 132 kV network within around 4 grid supply point zones. Now, we've got around 50 zones in total. So obviously, a study looking at 4 did not capture the full detail required for an in-depth study, but this did give us a forecast to establish an upper limit of curtailment behavior across annual profiles, since our high-hourly generation profiles were used in this side of the work. So just to summarize some of the limitations from our stage 1, which we wanted to address later on, the Transform study only considered 4 representative days, of which no generation profiles were considered outside the summer months. It didn't contain any geographic detail at this moment, and there was no consideration around demand reinforcement or new technologies such as vehicle to grid. In addition, the simple curtailment tool was at that point fairly hard to scale up. It was based in Excel, and it was very case by case. We looked at grid supply points individually, but we didn't understand the true demographic. But as I say, it did give us these 2 methodologies did give us an upper and a lower bound. So on the next slide, you'll see how we used these profiles. So if we could just click through the animations, you'll see that we arrived at two approaches, which gave us a minimum and a maximum distributed energy resource curtailment profile. And these can be essentially thought of as a boundary condition that we set within the power market dispatch model, which Baringa is running for us. We're using a model called Plexos, and it also considers other availability factors such as the weather and operational scenarios, including maintenance for key generation assets. And we also considered the flexible asset maximum export constraint scenario within that. So that's the amount of export that can be achieved in any hour period as a result of distribution network constraints. So once this was all loaded into Plexos, Baringa ran their forecasting and created 2 scenarios per forecast model. A scenario where assets can dispatch freely, there's no curtailment issued at all, and a scenario where assets are constrained. And so looking at the price difference and carbon difference between these 2 scenarios, we were able to forecast the overall benefit each scenario offered. So our next slide will share some of these findings. So under our lower bound scenario, the network curtailment scenario, which used Transform, the 12-year accumulated benefit to the system was found to be 324 million pounds at an average of 27 million pounds per year. The carbon saving benefit was a similar order of magnitude at 116 million pounds per year in total. Under the upper bound, the maximum constraint scenario, which used the simple curtailment tool, we found the benefit to be significantly higher, leading to a the volume of curtailment was found to be much higher, at around 20 terawatt hours in total, compared to only 1.4 terawatt hours in the network curtailment scenario. And this led to a much greater accumulated benefit of around £17 billion forecasted, with a carbon benefit of £753 million. With these findings in mind, and the limitations of our initial methodology more widely understood, we were able to be confident that the scale of benefit was there and was worth evaluating in more detail. And so we then embarked on our stage 2 of the project, which aimed to develop a more comprehensive methodology and results, which Kate will now walk us through.
Hi, everybody. As Lawrence said, I am going to use the next part of this webinar to talk about how we developed our methodology from stage 1 into stage 2 and some of the changes that we made in depth. And then I will be discussing after that the results that we've got from our stage 2 modelling and how they've changed and varied from what we saw in stage 1. So first of all, just going to highlight again some of the stage 1 limitations that we experienced and give you a brief overview of how we changed these moving into stage 2. So the first limitation that we saw in stage 1 was as the GB network is a winter peaking demand-based system, the profiles that we use in stage 1 to represent our 4 representative days were profiles that are used for network planning. Now, as we're a demand peaking system, this means that generation isn't particularly considered within those profiles, and they instead are more heavily demand based. This meant that outside of the summer months, generation wasn't really considered, and therefore all of our curtailment in stage 1 ended up being constrained to the summer months. In order to prevent this limitation moving into stage 2, we developed a series of improved generation profiles for wind and solar, and we increased our representative days from 4, so 1 for each season, to 12, where we had 3 within each season, so winter, summer, intermediate warm, and intermediate cool still. But within these seasons, we had a peak generation day, a peak demand day, and then an average day. We used in stage 1 a fixed rating of our assets, but we know in reality this isn't how the networks work, and in fact we ensure that there is sufficient capacity for demand, and therefore the asset ratings would not be static to our 2023 year and would in fact grow. This could limit curtailment and reduce the volumes that we were seeing if reinforcement is large enough for demand. So we considered this. We increased our asset ratings to reflect demand. We added additional technology profiles that weren't included in stage 1. This was particularly around V2G, and also how we addressed and looked at battery energy storage within the models and performed a sensitivity around this. And then the final, probably most concrete thing that we did is we took the 2 methodologies that we'd used in stage 1 and we combined these so that there was a single combined view of curtailment from the 400 volts all the way up to the 132 kilovolts of the distribution network. And then taking that singular view, Baringa, our project partners, assessed a curve around this of different variations of curtailment in order to understand what the benefit of preventing curtailment is if our best view were to be higher in reality or lower. I'm going to talk a little bit more in depth now about some of these changes and just show some of the actual methodology that we used. So the first one I'm going to talk about is our seasonal profile changes. So as I discussed before, we had 4 seasonal profiles in our first model, and in our stage 2 we updated this to 12. In order to do this, we took the simple curtailment tool, which uses a load profile for all 48 half hours and 365 days of the year. we did a series of analysis at EA Technology, and we assessed these profiles within the seasons to understand statistically how we could fit all of the 90 days within a season within 3 representative days. And from that, we ended up with some load profiles, as the one shown here on the screen, where you have both demand and generation for different days. So you have generation for demand days and high generation days for the 2 types of generators. What we saw was that there were general trends around the seasons. For example, a peak generation day in winter tended to be reasonably low solar, particularly in the UK, but would be very high wind, whereas a peak demand day would be low of both. Whereas in the summer, we saw high solar in both peak demand and peak generation days, but the wind varied on to a peak demand day and a peak solar day, because we would see less generation on a day in the summer that's windy, but the solar patterns tended to be the same. From this, we could take these into our model and analyze the 12 representative days. And the hope was that we would see generation outside of the summer months that was being curtailed. We also updated the battery profiles used within Transform. We, in stage 1, took the ideology that batteries do exactly what you don't want them to do on the network, which again is a network planning perspective. We know that batteries can operate faster than the signals that the networks can send to them using network management. So in order to ensure that there is sufficient capacity on the network, we have to assume that they are acting as generators when the demand is low, and they're acting as they're charging when demand is high, so that the network has sufficient capacity for the batteries to exist. But in an economic perspective, this probably isn't how batteries are going to work, and they will have much variable profiles responding to price signals in the network. Also, domestic batteries won't work to price signals at all, and they will simply be charging when prices are low during the nighttime and demand is low, and then they will be removing some of peak load from houses during peak times sort of in the afternoon. So we developed 2 sets of profiles for these 2 different batteries, a domestic profile for each season, and also the same 12 representative days that I talked about in the previous analysis. And then what we could do in this study is we could look at a situation where the batteries acted as they did in stage 1, and one where they had this more variable load profile, and we could compare what that did to our results within our analysis in our final report. The next update that I want to talk about is our considerations around the demand reinforcement from the LV network to the 3366 network, where we consider demand reinforcement. So we looked at our network and we looked at the assets within our network, and we said that if a constraint was met in our transform system that was due to demand, we would allow whatever increase in asset ratings that the modeling predicted would be needed over the next 10 years, and we allowed that to take place. If the constraint that was met was a generational constraint, we kept the assets fixed at what they were before the constraint was met. And this meant that in our modeling, every time our assets reached a demand constraint, they would increase in rating based on a solution applied within Transform. But if it was a generation constraint, they weren't. And this reflects what happens in reality within our network, that actually the distribution networks in the UK need to ensure that there's sufficient capacity for demand, but the same constraints don't necessarily apply for generational needs, and they're much more demand focused, which meant that we were getting a far more representative view of the network based on the methodology we were using to analyze the load that was coming out, and therefore the curtailment. So from this and our updated methodologies, we then combined the results from Transform that we just updated and with the simple curtailment tool. Within the simple curtailment tool, we increased our sample size from 4 GSPs to 17. We looked at a series of constraints from different attrition rates, as well as including transmission constraints. The guys at NGED worked really hard to write new scripts that meant that scalability was easier, and we could do this on an increased sample of GSPs, as well as get the data out quicker and analyze it to a higher standard, and look at a larger volume of constraints as a reflection of that. We then took the 17 GSPs, analyzed the expected capacity or the anticipated capacity on GSPs of other networks and other license areas within the UK. And we scaled the volume of curtailment seen at the simple curtailment tool to be reflective of the whole of the UK. We then combined these studies to get a singular best view of what we think curtailment would be based on all of these assumptions that we'd updated. This best view went into the power market modelling, as Lawrence has already explained, and this again has had some updates from stage 1. So in stage 2, we're now looking at a single best view of analysis for one run of Plexos to determine the value that this will bring in the reduction in the wholesale cost. Not only that, but we are looking at the whole year, whereas the network modeling analysis was constrained from June to August last time, whereas this singular view now will be of the whole year, which means we should get a more representative idea of what's happening with generation outside of those months. Baringa are doing a benefit curve analysis, as I've already explained. So they're going to scale the best view results of curtailment down to percentages and up to percentages, in order to analyze what the cost in carbon and pounds will be if, from our best view, in reality, we were to actually see more curtailment or less curtailment. What this will allow NGED to do is actually assess areas that might be have higher volumes of generation on or lower volumes of generation on, and therefore determine how much value targeted reinforcement would have on these areas. And Baringa are also doing an assessment of the impact of ancillary services and how curtailment in our network impacts them. So I've given a view of the methodology updates that we've made going into stage 2, and I'm now going to talk a little bit about what curtailment we forecasted as a result of these moving into stage 2. So firstly, we saw a much larger spread out of the year of curtailment between phase 1 and phase 2 with our updated methodology changes. Not only that, we also saw a larger volume in general because we were just modeling generation better in all of the seasons. And we had average days that also included generation instead of just a singular peak generation day, which was on very specific days within the year. So this was an increase in volume and also breadth of curtailment that we experienced. We really saw an increase in curtailment moving from our 2028 study year. So yeah, it's probably worth mentioning. We did 3 study years as part of this analysis: 2023, 2028, and 2034 were the 3 years that we looked at. What we noticed is moving from 2028 to 2034, we saw a big increase in the volumes of curtailment that we were experiencing. And this is a reflection really of the volumes of growth that we're seeing sort of over the next, and we expect to see over the next 10 to 12 years, and how there is going to be a sort of tipping point where we have more occurrences of our assets within the network breaching the limits that they have because of generation as opposed to demand. Based on our modeling, we analyzed that by 2034, we forecast, based on our assumptions, 8.5 terawatts in 2034 of distributed generation will be curtailed, which from a UK perspective is enough electricity to power 3.2 million homes within that year, which is a considerable amount of customers being affected, and that if we release this generation could have cheaper electricity as a result. So we then analyze the electricity, the curtailment from a bit more of a specific generator type assessment. So these are the curtailment volumes for the combined 400 volts to 132 kilovolt networks. And what we saw is in 2023 and 2028, our other category, which is mainly gas generators, dominated the curtailment. And this is to be expected because it's a large portion of our energy mix. By the time we got to 2034, it was actually solar that ended up being the largest contributor to curtailment, which is expected as we're going to see a large amount of solar, domestic solar being, we expect to see a large amount of domestic solar coming onto the grid as we sort of move over the next 10 years. Wind and battery, we saw less volumes of curtailment, but this again is due to the volumes that we expect connected with issues in the UK, such as the England ban on onshore wind, which has just been lifted. When we look at this from a voltage level perspective, we saw at in 2023 and 2028, a large amount of curtailment being restricted to the 132 kV level, which again is explained by the fact that this is dominated by large plants. Whereas by 2034, we see a lot more of this on our low voltage networks or our 400 volts network, again, as a reflection of domestic solar. What it is worth talking about here is that where we talk about LV curtailment, we're not saying generators responding to A&M signals. We're saying that the network would reach sort of volt rise constraints and the assets would trip off and therefore be unavailable to the network. And this real switch in dynamic as we move from 2028 to 2034 is really important because the networks want to make sure that people don't get disenfranchised and really want to commit to the energy transition. And knowing that your solar on your roof might end up tripping off is going to really put people off wanting to invest in that. And that's not what the networks want. They want people to get on board with the net zero transition. So that's my update on the methodology and the results. I'm going to pass back on to Lawrence now, and he's going to talk about what's next for our project, and then to you, Gendra, to conclude.
Thanks, Kate. That's a very, very interesting overview of where we are now. And it's quite an exciting point in the project as we are beginning to reach the end of our results gathering stage. So if I could just go to the next slide, please. Yes, so by January of next year, we will have completed our Plexos modelling and produced our final report. So Baringa are currently working hard getting cost curves and voltage level sensitivity studies complete. This is going to allow us to disaggregate that total benefit which we predicted in stage one and understand where exactly the benefit could be found. So what are the parts of the network that need to be where's the headroom needed most, basically? Where would have the greatest impact on the overall costs? And as a result of that learning, we, as the sort of future capability team, are beginning to think about what are the next projects that could test these sort of assumptions. What are the areas which we need to increase capacity, sort of most concentrated around? What projects do we need to do? So the learning from this project is really going to help direct that future work. And within the wider business, so outside of the future capability team, we see this as sort of being a financial justification for improvements in A&M. So I put a note in the Q&A box here about how our current A&M system operates, but there are areas that could be improved to get a slightly less pessimistic study and a less pessimistic view of curtailment. So generation could be curtailed less if there's some improvements to be made there. And it could be a means for us as a network to justify new capital projects to increase capacity. If we're able to position ourselves with this new line of justification, saying that, well, if we spend some money to increase the capacity, it will have a much larger consequence to the wider system. It could be something for us to do there. And then hopefully in the longer term, we'll begin witnessing some of the benefits that this early forecasting piece of work has sort of investigated, if we are able to make some of these cases to the business and the wider regulation space. So I think that's been a really interesting summary. I know Yugandhra is going to give a summary, but thank you very much for your attention. And I'll hand over to Yugandhra now.
Thank you both. Thank you, Kate and Lawrence. Just to summarize, preventing curtailment of DER within the UK network. So there is a demonstration that will also decrease the wholesale cost. And as Lawrence was saying, that component of the wholesale cost is increasing in the bills. And that is good for environment also. So yes, that has, if we think holistically, it has many advantages. But the key is the correctly forecasting, that how the DER uptake will actually result into the likely curtailment, and ensuring that they connect to the network, and how do we connect it? What is the best mechanism to do that? The curtailment of renewable generation need to be minimized and should be at the last resort to maintain the system security, without doubt. Flexible or curtailable connection is one of the tools to manage the system risk. And as I mentioned in the beginning, the Australia, we have the CV value, which actually helps a little bit in making the business case decisions or the justifications for AER, the price reset submissions, which I'm sure UK also does for ED things. So I think that is probably the end of this thing. And while I encourage all of you to type your questions, if you want to ask anything, I will actually just, let me see if there is a question here. Yes, so there is a question here. Let me just see. So with the increased curtailment due to congestion in the network, it must be difficult for generation or BESCOM proponents to perform economic viability analysis of their plant, as the level of curtailment of the life of the plant is very difficult to predict. Any comment? So maybe Lawrence can best answer that.
Yeah, I mean, I certainly agree with the point made in that comment. We are providing curtailment forecasts to generation customers as popular. There's two options for customers. Ofgem, our regulator, has produced a methodology which gives an initial view. We think that that methodology is maybe slightly pessimistic. So we've developed a separate methodology that we were using within this project, the simple curtailment tool, which provides another forecast for generation customers. And the DSO is also working with one of the other UK networks, UK power networks, in fact, to try and see what improvements might be made. But you're completely right. We do see generation customers currently sort of receiving their curtailment studies and rethinking the sort of economic viability of such projects. It's in public domain. There's been curtailment forecasts issued to generation customers, sort of saying there's 99% of their export will be curtailed, which obviously wouldn't make sense. So at a very local level, there's quite an important impact for developing curtailment forecasting approaches, but also at this wider whole system level, we see value in improving our forecasting capabilities too.
Thanks, Lawrence. And for the benefit of the local audience, I would like you to explain a little bit on difference for headroom and hosting capacity, and how, because this part, especially Australia, is actually talking of hosting capacity and knowing that through the dynamic operating envelope. So just see hosting capacity using DOE or headroom using what, if you can explain that perspective.
Certainly. So in this project and sort of broadly within our team, we see the hosting capacity as the sort of capacity of the network. You can have a summer capacity, which is often slightly lower than the winter capacity because of solar heating that takes place just due to the weather. So we say this is the capacity of the network, and then at any given point of time, it can be operating as a certain sort of power consumption, power demand, and then the delta between the capacity and the current sort of demand is the headroom. So it's what's the difference? What extra capacity is there that could be used that's not currently being used?
So, and how is that calculated if dynamic operating envelope is not used at the moment in UK?
So the assets rating, so the hosting capacity rating is known, and as I said, this does vary during the year. And we can see through our SCADA systems and sort of power quality monitoring that we're rolling out the sort of real-time loading of various assets, whether that be a circuit breaker feeder, a transformer, or an overhead line monitor we're trialing as well. So we've got a relatively good view of our 11 kV to 132 kV sort of power demands in real time. And so we can sort of compare those two to sort of evaluate that the headroom.
Okay, so that means it will require the LV, means like monitoring.
Yes, so LV monitoring is something that we haven't had so much in the past, but we operate in price controls in the UK, and our current price control ED2 is seeing a vast rollout of LV monitors. We have around 160,000 secondary substations, of which around 55,000 are ground-mounted sites. Of those 55,000, we're planning to install around 15,000 sensors. So we should have a relatively good coverage of LV monitoring, and we're targeting sites which we have less data about, or sites where smart meter data is unavailable, or some sites where we think we're almost breaching capacity for that rollout. So targeting the worst areas first.
Thank you for that. And coming back to the connections, like when we are saying this is curtail level connection, is happening like when there is an offering from the to the customers saying this is kind of connection you can have?
Yeah, so when a customer comes to us with a connection request, we would offer them a traditional connection request, which may include the reinforcement required to allow them to export. If significant reinforcement is required, this could be a sort of seven-figure sum, so millions of pounds. Whereas if customers were willing to accept that for some points of the year they weren't going to be able to export as free as they wish, they can accept a curtailable connection with an expected reinforcement date. So they'll connect for now, being curtailed, but with the knowledge that in the future the wider upgrades to the network will allow them to dispatch more freely going forwards.
And Kate, in terms of actually, it's all question of network forecasting and planning and forecasting tools. Now, to get the right profile for generation and load, especially considering the EVs and V2Z, what is that how you're going to generate those profiles which you think will be more accurate for the stage 2?
Yeah, so we tried to use, and this is the difficulty of using a parametric model, we tried to use as representative samples as we could. So for V2G, for example, we took this from another project that we'd done with NGED, where that was a customer-driven vehicle-to-grid charging project. We took the data directly from that project to look at how people were participating within the market signals, and that's how we produce the V2G profiles for that assessment. When it comes to generation, it's a lot more difficult, particularly using a parametric approach and representative days, because As I imagine everybody knows, it's constantly in the news when you talk about renewable energy. The weather changes every day, which means that these profiles change every day. In an ideal scenario, what we would have is a curtailment forecasting tool that could look at every day, every hour of every day, every half hour of every day differently. It would look at the network from a connectivity perspective, and it would be able to calculate your curtailment at every half an hour, right the way down to the LV level. But I don't know of any computers that would have the power to do that in a useful amount of time. So what we have to do is we just have to make sure that we're doing it as representative as we possibly could. So for this project, when we decided on the 12 days, we assessed them statistically to make sure that they matched with what NGED were using within the simple curtailment tool, which is a full year's worth of generation. And that meant that we could at least get 2023's data right. Now, I guess what poses the question is, and I don't necessarily have an answer to this one, but maybe it's something that we need to think of when we're thinking of these curtailment forecasting tools. How are those profiles going to change out to 2034? You know, we know the weather's changing and we know the climate's changing. So something that we really need to assess is if we are going to start forecasting and it is needed, better curtailment on generators, we are going to have to factor in that the weather might not be as it is today. And they're going to be important considerations that we have to make when we're developing these forecasting tools for generators. But that's a question that we're going to have to think of when we try and develop this tool.
Yeah, it's a difficult science. It's like weather forecasting. It has become better over the last 20-30 years. So hopefully our forecasting, especially the profiling the load and generation now going forward, very, very difficult, very challenging. Not that it will not happen, it will happen. Look, here I want to, bring this, webinar to a close. I want to thank all the attendees and also my both colleagues from UK. I know it's 11 p.m. in night time, almost midnight there. So thank you, Kate, and thank you, Lawrence, and thank you everyone for attending. Thank you so much.
Thank you as well, Yugendra, for hosting us, and Callista for organizing and doing all of the behind the scenes work.
Thank you.
Cool. Thank you.